All right, good afternoon and welcome to the presentation for Group 5, the Police Scuba Boat Enterprise. I will begin this presentation by introducing each one of our group members and thanking our mentors. I will then discuss the principal particulars, class rules, and mission system requirements. First is Jeffrey Basti from Brooklyn, New York, who plans to pursue a career in maritime patent law. Ashley Farrell from Chino, California, plans to pursue a career in autonomy, focusing specifically on USVs or AUVs. Casmir Lesiewicz from Riverhead, New York, plans to have a career focusing in sportfish design. My name is Ella Wilson. I'm from Cabot, Pennsylvania, and I plan to pursue a career in sustainable yacht design. We would now like to thank each and every one of our mentors for their invaluable guidance and advice during this design process. The primary objective of Enterprise is to provide a fast, stable platform to support the scuba team's activities in and around the waters of New York City, up to a distance of 10 miles offshore in most weather conditions. There were several major mission requirements that drove this design process. The first is a high level of redundancy. Due to the vessel's response of emergency situations, it's imperative that there are as few points of failure in mission systems as possible. 360-degree visibility from the pilot house ensures the monitored safety of everyone on board and in the water. Fendering, structural rub rails, push bars, and the like allow for the vessel to bow up to other vessels or to piers. Deck space is important not only for the storage of the 15-foot Zodiac rib, but also to allow for helicopter operations to take place on the aft working deck. Additionally, this allows for injured personnel to be maneuvered around the vessel without obstruction. The deploying and recovering of divers, victims, and said rib is part of the day-to-day operations of the team. A 1.5 long-ton telescoping crane is also to be included on the vessel to assist in maneuvering the rib and to remove larger objects from the water. Finally, the CBRNE, or Chemical, Biological, Radiological, Nuclear, and Explosive Detection Equipment, is not only necessary for the safety of those on the vessel, but for the safety of those in and around New York City. This vessel is classed under Class NK, and the two major sections of the rules that were consulted during this process were the Class NK rules for the survey and construction of steel ships. Additionally, the Class NK rules for high-speed craft. The stability analysis was carried out in accordance with the IMO Intact Stability Code, and all equipment for life-saving and firefighting was placed in accordance with 46 CFR. The principal characteristics of Enterprise can be seen above. She has a length overall of 65 feet and a length between perpendiculars of 55 feet, a beam of 19 feet, depth of 10 feet, and draft of 3.5 feet. The frame spacing on the vessel is every 2 feet. This vessel was designed with a patrol speed of 12 knots, cruising speed of 22 knots, and a sprint speed of 30 knots. I will now pass the presentation off to Ashley to discuss our hull shape and general arrangement.
Thank you very much. The leading aspect of our hull design was based primarily upon the speed and maneuverability requirements provided with our vessel. In order to develop the shape that you see here, we used an Orca 3D developed planing parent hull, which we later modified to our specific requirements. On board, you will find several details that we have included, one of which is a chine, which helps increase our lift and assists us in a planing condition. You will also find a flat bottom, which increases our maneuverability, similar to that of a jet ski. This comes with the added benefit of being able to lower our engines and water jets, which lowers our draft and therefore our required power. Finally, we have a V bottom close to our bow. This allows us to reduce slamming, particularly in high speeds. Here you can see our inboard profile. Towards the aft end of our vessel is our machinery space, where you will find our generator, engines, propulsion system, and other equipment. Within the accommodation space, we have a designated dive equipment storage and locker area. This is where divers can get suited up and take their equipment off in a temperature-controlled area with comfort. In the event of 24-hour operations, primarily conducted in emergency situations, bunks and lockers have been included to allow for divers and operators to get the rest they require. At our bow is our fendering and staircase system, which allows our vessel to be able to bow up against other vessels and piers and allows for easy boarding and disembarking from our vessel. Here you can find our munitions locker for police operations. And below our accommodation space is where you can locate our tanks. This is our main deck. On board, you will find a computer workstation inside the pilot house that allows for operators to be able to communicate with individuals on land and keep their paperwork organized. At our aft end, you will find a swim platform where divers can safely enter and exit the water, as well as being able to recover victims or objects from the water. In the event of an emergency, we have a designated airlift zone where a helicopter can drop its basket and a victim can be safely secured and brought to safety. On the starboard side of our vessel is a rib, which can be quickly deployed and recovered using the winch forward of it or the 20-foot crane located on our sun deck. On board, we have the storage capacity for up to 12 SCUBA tanks, 4 of which are located on a bench, which allows for divers to be able to quickly get suited up and take their equipment off with ease. Inside the pilot house is further dive equipment storage for objects that need to be easily available and organized. Here you'll find our charting table where we have charts, maps, graphs, and other vital paperwork located easily and organized near our navigation and control center. Our navigation and control center is located at the forward end of our pilot house. From here, operators are able to have a 360-degree view of the world around them. Operators can also drive the vehicle from the sun deck above. We also have a designated rest area for VIPs, operators, divers, and victims to rest and recover within a temperature-controlled area. The storage space inside the couches are where vital life-saving equipment is located. I will now invite Jeff to the stand to talk about our weights and centers.
Thank you, Ashley. I will now discuss our weights and centers as well as our intact and damaged stability cases. A weights and centers spreadsheet was created for this vessel, which includes all items on board that add to the weight. The lightship and full load displacements for this vessel were calculated using the spreadsheet. The lightship only includes the hull and all items that are installed permanently on board, as well as items that may be removed in its everyday missions. The full load displacement includes the lightship as well as the deadweight items. The deadweight can be defined as any personnel, tank loading, stores, gear, and tenders on board the vessel. The general arrangement was used to determine the distances of all items on board the vessel in reference to station 0 for longitudinal distance and baseline for vertical distance. The weights of lightship items on board the vessel were taken from manufacturers and vendors, as well as such as Caterpillar for the engines and generator and Hamilton for the jet drives. The hull and weights of bulkheads were determined using a material selection of 1/4-inch 5083 aluminum for the plating and utilizing the surface area feature in Rhino. Additionally, the weight of the longitudinal stiffeners was determined after the midship section was completed and the size and number of stiffeners was known. The lightship was then calculated by summing all the weights, LCGs, and VCGs of items throughout the vessel. This table displays the summary of lightship weights installed on board the vessel. The vessel was broken up into several sections, including the pilot house, forward main, aft working deck, lower deck, machinery space, and tanks. This allowed for an organized spreadsheet to ensure we did not miss any items on board when calculating the lightship and deadweight items. The LCG and VCG of the vessel were then calculated using a total displacement and sums of the values. A margin increase of 35% was used to accommodate for all other items on board, such as auxiliary machinery, piping, and wiring that were not accounted for at this point in the concept design. The full load conditions include all deadweight items that are expected to be present on the vessel when completing its missions. The full load departure condition includes 98% loaded fuel, freshwater, and oil tanks, as well as 10% loaded sewage tanks. The full load arrival conditions consist of 10% fuel and freshwater tanks, as well as 98% sewage and oil tanks. A full load of 98% for the tanks is to represent its full capacity. If tanks are filled to full capacity at 100%, they would overflow, and this could cause problems, especially with fuel or oil tanks. 10% is left in empty tanks to prevent loss of suction to a pump. Lightweight condition is the same as previously stated, no tanks and no deadweight items on board the vessel. These conditions were used to develop the general hydrostatics of this vessel and represent them at different points in their mission. It is important to test the extreme conditions the vessel may be in, which is leaving the dock fully loaded and returning to the port for this case. As you can see here, the general hydrostatics and the lightship loaded departure and loaded arrival conditions are listed. As is expected, the GM of the vessel is higher in the lightship condition when compared with the loaded conditions. The LCF draft and LCG of the vessel are in reference with the aft perpendicular. General hydrostatics was the computer program used to compute these hydrostatic values. The draft was determined by solving through this program, and Rhino allowed for the integration of tanks for ease of loading and unloading throughout this project. Now I'll discuss the stability of our vessel. The IMO and Class NK rules were both used for the intact and damage stability requirements for this design, specifically the high-speed craft sections. We only focused on the displacement mode for this vessel as it was appropriate during this phase of the design. The intact stability was created using GHS to determine the GZ curve of the vessel at each loading condition. The GZ graph on the right is of the full load departure condition. The righting arm curve, red and linear, represents the lever arm applied to the vessel and when at the corresponding degree of heel. The same was done for the full load arrival condition. The same was done for the full load arrival condition and loading conditions. To confirm that the vessel meets regulations, each loading condition was run through the program and compared with the values provided by IMO and Class NK. According to IMO, the righting arm must be greater than 0.2 meters at an angle of 30 degrees. And according to Class NK, the maximum righting arm is to occur at an angle greater than 15 degrees of heel. It was determined that the Enterprise does meet all these requirements. For damage stability, we calculated the floatable lengths curves for the Enterprise, and it was developed in GHS. Permeabilities of 0.85 and 0.95 were used for the floatable length curve. The bulkheads along the vessel were inputted into GHS to discover which compartments could potentially be an issue if the vessel began taking on water. It was found that the main compartment were to take on water, the vessel would be in danger. This section, where you can see the bulkhead triangle intersecting the 0.95 permeability, suggests that the vessel would be in danger if this point is reached. In the next tier of the design, another bulkhead between the forward collision and the tank room bulkhead would be included. This would solve the issue. Now I'd like to invite Casmir to discuss our major systems.
Thank you, Jeff. This slide lists a few of our major systems that required engineering attention during the design process. I will now discuss a few of these systems in more detail to explain our design decisions. For the propulsion system, we began with a parametric analysis to size the engines. It originally indicated that we required approximately 2,000 horsepower. We then confirmed this result using Orca, which indicated a slightly lower value of just over 1,900 horsepower. However, this value does not necessarily include all necessary considerations. For the engine, we selected the CAT C18. Originally, we had sized two larger engines, but they fell under EPA Tier 4, which required an additional CEM that was too large to conveniently fit within our vessel. For this reason, we selected 3 of the smaller C18s that fall under EPA Tier 3. An added benefit of this decision was that it added redundancy and flexibility to operations. When operating at the patrol speed, 1 or 2 of the engines could be run instead of all 3 at a more efficient speed. However, when additional speed is required, all 3 engines provide sufficient power to reach that 30-knot top speed. These engines are also manufactured in the United States as required, and help us to meet our sustainability requirement as they are capable of burning B20 biodiesel. Biodiesel has very similar properties to diesel fuel, except that it is considered to be more environmentally friendly because the emissions that come from burning it are offset by the biomass that is grown in its production. However, it does come with one added drawback, that it is prone to absorbing water, so we made sure to include water separators in our fuel system. For the actual method of propulsion, we selected the HM422 Hamilton water jet. The water jets offer superior performance at high speeds and are very maneuverable. They're also safer to operate around divers and can function in shallow water. Finally, they've been shown to reduce vibrations as compared to traditional propellers. For the electrical system, we selected the CAT C4.4 generator. It can also run on B20 biodiesel and was sized based off our load analysis, in which we considered idle, transit, mission, and emergency conditions in both the summer and winter. We also included 6 house batteries that provide additional redundancy and flexibility in operations because many of the systems can be run off of batteries without having to run the generator. This can be seen on our one-line diagram. Systems such as the radar, windlass, and winch can be operated purely off of batteries. This means that our vessel can function effectively without reliance on the generator. When conducting dive operations, the primary point of deployment recovery of divers is designed to be the swim platform. It can be accessed via 2 stairways so that divers can access this area easily while wearing their equipment and so that the crew can assist divers without getting in the way. The second method is the rib. It can be deployed via the winch or the crane and is useful for accessing areas that are difficult for the vessel to get to. The winch is aligned with the rib so that it can be easily deployed off the stern of the vessel by pushing it on or off of the tracks. The crane is aligned with the rib, but it was likely to be slower. However, it may be more effective in certain conditions. It has a reach that extends 15 feet beyond the side of the vessel and can hold over 1.5 long tons. Finally, divers can operate out of the rescue wells. These are positioned away from the wash of the water jets and provide additional flexibility during dive and rescue operations. We also required a 10,000-pound safe working load towing bit, which is located on the aft working deck. Finally, we included fendering, which is useful for bowing up to piers, bulkheads, and other vessels. Often, this is the most convenient way of accessing these locations. There's also a staircase on the bow that helps with accessing taller structures. Now, as you can see, the actual section modulus for our midship section is significantly higher than the required section modulus. This will help our vessel to withstand some of the more significant loads that it will be subject to. One such load is hull slamming, which is likely to place significant impact loads on the hull. Another less traditional load is towing, which must also be considered. Finally, bowing up to piers, bulkheads, or other vessels is likely to place significant compressive loads on the hull. This leads to concerns with buckling. Now, our longitudinal framing system and additional structure should help to minimize these issues. Now, I would like to invite my teammate back up to the podium to take questions. Thank you.
On the Delta thing, the flat that you guys had, two questions. One, would you consider directional stability at all with the vessel, especially with the water jets? You don't have any flooding, kind of like keep you on track. Is there a problem in high-speed runs? And then again with the Delta Bay, how did you guys consider it in your resistance to propulsion applications? Or its effects on resistance?
So the question was, how do we consider the directional stability of the flat section on the bottom of our hull towards the aft end? And how did this impact resistance and propulsion calculations? So this decision was actually inspired by the current NYPD vessel. It also has a flat section towards the aft end, and it seemed to be sufficient, like their directional stability and their performance was still sufficient with that included. Ours is a little bit larger, so that is something that should be looked into further if this design continues. terms of resistance and propulsion, it was mainly just done using parametric analysis to begin with, as I said. And then the Orca was used, which didn't include that flat section originally. And it may have an impact, but it's not something we looked into significantly.
Great job, guys. I know I asked you guys to work a lot on the bow of the boat, because a lot of what we do at work is to transfer gear and equipment from the boat, from the vessel to shoreside or another vessel, and vice versa. And certainly that might be personnel and or equipment. And I know you worked a lot there. Can you touch a little bit about how you solved some of that problem, and also with the tidal influence, and different areas that I have to, potentially put people on. Sometimes the barges we battle up against are quite large. What you guys did to influence that?
Okay. So the question was to elaborate more on the fendering system on the bow. I'm actually going to go back to our inboard profile. So we actually had it go down a little bit more than the current vessel that you have. So it allows for more surface area that's going to be attached or being pushed onto with like a pier or some type of object or ship. And then the stair actually goes down because it helps with, you can get into your anchor locker and it's not fixed anymore. So you can like really get in there and work in there. And your second question, I'm sorry.
I believe that answered it. I was just asking you what you did on the bow as far as pushing up on objects and protection there, and allowing you to marry up against those different various items. It's never the same thing, whether it be like discussed in the slides, whether we're married up against a pier, another large vessel, or maybe a small vessel, or a low pier or a high pier. It just changes every time based on whatever the 911 call is and our mission. So I didn't know how you were able to help me with that, and also I wanted to take a look at that stair. And I'm not quite sure with the designer, it kind of folds into itself.
So it folds forward. So the entire stair, it'll just fold forward over the bow, and you can access the anchor chain locker.
Gotcha.
I would also like to add on to that our structural stability analysis did account for the high pressure of the forces being placed when bowing up, which was a significant margin.
The swim platform, as we talked about, getting divers in and out of the water, even victims when they're, whether they're not injured or injured. Was that, I didn't really hear it. Is the swim platform raised and lowered down to the water?
The question was, is the swim platform raising and lowering or fixed? In our design, the swim platform is a fixed structure that will not move in order to reduce the opportunity for failure. Something that was noted during our ship visit is that their current design is not operational because of issues with the hydraulic system, and we wanted to reduce points of failure.
You know how high above the waterline that would be, or what is there?
The question is how high above the waterline this swim platform is, and above the waterline, I believe it's less than a foot. The numbers aren't in front of me at the moment, though.
I believe it's only several inches, maybe 6 inches. It's very close to the waterline.
Additionally, with the raising and lowering swim platform, it is something that we did consider, especially early on in the design process. But with the water jets, we tried to keep the swim platform as low as we possibly could. And this was limited by the placement of the water jets and the buckets that have to come up. So even if we could lower the swim platform, we would only be able to lower it a couple inches, essentially, just because it's limited by the position of those water jets.
For reference, the box labeled water jet, which is our outboard jets, the top of that box is approximately where the water line is.
I was just interested, you sort of, but in the, you don't show plans, you would be minimum 3 engines. Is that something you looked at? How you fit 3 engines in a 20 wide?
So the question was, how did we fit 3 engines in a 22-foot wide boat? We did look at this. We did make sure that they fit on our full GAs, which you can see in the hallway actually afterwards if you'd like. They do fit. They are spaced closer together, but they are also inline 6 cylinder arrangement, which makes maintenance on the tops a little bit more convenient rather than trying to squeeze in with the V configuration. But they do fit.
Why did you decide to be on?
So the question was, why did we decide on longitudinal framing rather than transverse framing? The big driving factor behind that was that we do have to bow up to structures, and sometimes you put pretty significant force on there to really hold the vessel in place. And we wanted the longitudinal framing to help with reducing buckling.
Can you talk a little bit more about the selection of the control speed being 12 knots and how that may be compared to the minimum planing speed or displacement speed?
So the question was, can we talk a little bit more about our speed requirements and how that compares to our planing values? So our operational profile was something that was given to us in this design project. So I believe we're 90% at the cruising operation situation and then 10% at the sprint speed. And I want to say we start planing around 9 or 10 knots off the top of my head. So we should have no problem planing at 12 knots.
Two questions about your engine selection. At C18, what rating did you choose for that selection? And also, when choosing the engine, was there any consideration of commonality with perhaps the other vessels in the organization's fleet? That may have some benefits of going with a cat versus another kind of engine.
So the question was, when selecting our engines, did we consider the rating? And also, did we consider having commonality with other vessels in fleet? In terms of rating, we made sure that we use like the EPA Tier 3 and the IMO Tier 2, which they fall under. If you're talking about like horsepower or any of those requirements, or for those, I think we had, I think there were 715 horsepower, if I remember correctly. In terms of commonality with other vessels, we were somewhat constrained by the American built requirement. So we didn't take that into consideration, but they are pretty common and parts are readily available. So it shouldn't be a significant issue.
Something else that we took into consideration when choosing the engines was making sure it can work with B20 biodiesel.
Couple of online questions. Did you consider the operation of the water jets and the fact that you have divers in the water?
The question is, did we consider the operation of the water jets with the combination of divers in the water? The answer to that is that we were using the water jets as a safety system without being able to, or to avoid having propellers in the water while divers are actively operating. It should also be noted that that is the current system in place with their current vessels.
Additionally, we do have the rescue wells, which are positioned further forward on the vessel that keeps divers out of the wash of the water.
Another question asking about the arrangement of the rib. The question was the heaviest part of the rib appears to be over the stairs. It's an unusual design choice. Is there some feature that's driving this arrangement?
So the question was to elaborate more on the rib and if it, because it goes over the stairs, if it is going to be an issue. So the rib actually will be on a cradle, which is on a rail system, and then it can be lowered into the water and then pushed off the cradle. So there's actually a structure that it will be sitting on that will reinforce it. That will be structured.
Got it. And next we already answered about the flat area aft. What was the basis of the 2-foot frame spacing?
So the question was, what was the basis for the 2-foot frame spacing? That initially rose from just other vessels that were similar and prior experience with aluminum boats. It really wasn't an issue. It was kind of something we picked arbitrarily early on based on experience. And then as we got to our structural analysis, it proved to be effective. So we kind of stuck with it.
It was also based significantly upon current operation of vessels, primarily from parametric.
Okay, thank you very much.